Hi there, and welcome to Chapter 2.2 from Stevens's Matrices, Vectors, and 3D Math. In this chapter, we're going to do vectors in space, and what I mean by that is vectors in 3D. And we did vectors in 2D in the last chapter, so a lot of this provides just a natural extension from 2D to 3D. But just going to the 3D coordinate system is a little tricky, so I want to go through that first. And as I do that, I guess I'm going to switch over to full screen mode here. Alright. Okay. So what I have here is what's known as a right-handed coordinate system. Right? We have a positive x-axis here, positive y-axis sort of going back into the page, and then the positive z-axis up here. It's called a right-handed system because if you were to stand here at the origin, your right hand would point along the positive x-axis. Right? And with these axes, x, y, z, and axes, break up three space by, let's see, three different planes. We have the xy plane that goes right along here. And then we have the the xz plane, which is the plane on the actual paper. And then we have the yz plane that's sort of perpendicular to the paper and goes in along the y-axis there. Okay, and a point in 3 space is denoted with 3 numbers, an x value, a y value, and a z value. And when you plot those points, you go this far along the positive x-axis. Then you go this far parallel to the positive y-axis, and this far parallel to the positive z-axis. And I'm going to plot these points here, but beforehand I'm going to put some tick marks on my coordinate system here. So I'll just do some along the x-axis, some along the y-axis, some along the z-axis, and I'll do the negative tick marks as well. Okay, so suppose I want to plot this point P, which is 2, 3, 4. That means I go 2 units along the x-axis in the positive direction. Then I'm going to go 3 units parallel to the y-axis. So I'll go 1, 2, 3. Alright, and then I'm going to go 4 units directly up parallel to the z-axis. So that's 1, 2, 3, 4. So this is that point P, 2, 3, 4. Right? P, 2, 3, 4. And you can sort of see where it's sitting. It's sitting in that sort of first quadrant where everything's positive. And then if I wanted to go, and I'll erase some of these dots that got me there. I don't want it to get too messy. So now let me plot the point Q right there. -4, 1, 3. So I'm going to go 4 in the negative direction along the x-axis. So that's 1, 2, 3, 4 in the negative direction. Then I go positive 1 in the y direction. And then 3. 1, 2, 3 in the positive z direction. So that gives me my point Q, which is -4, 1, 3. Now suppose I wanted to connect P and Q. I wanted to draw the line segment from P to Q. If I just connect it like that, it doesn't help sort of create the picture. I can't tell which is in front, the z-axis or that line that I just drew. And the thing to notice is that the z-axis is sitting right here at y equals 0. But this point, P, has a positive y value, so it's in the positive y direction. So it's behind, this point, P, is behind this z-axis. And then if you look at this for Q, that point has a positive y value as well. So it too is behind the z-axis. So this whole line that I just drew, this line here, that should be passing behind that z-axis. So the way to give this sort of a realistic look is I just break my line at that axis. Alright, so at this point it now looks like that line is behind the z-axis. So that's just a little trick of how you make certain objects in 3D appear behind other objects. When I mean behind, I mean sort of deeper into the page. And by no means do you have to be a good artist in order to do well in this course or with this book, but it does help to try to sketch these things and draw these things just to learn how to picture things in 3D, because we're going to be dealing with a lot of 3D geometric objects, and it's good to be comfortable with what they look like in a 3D coordinate system. I'm going to let you work on plotting the points R and S. You can use the your book for that, and then try to connect these 2 points. And in that case, you have to determine whether or not that that line passes behind or in front of the x-axis. So it's a similar little game, and the more you just sort of play around with plotting things in 3D, the better you get at it. So I recommend you just play around with it. It's not essential for knowing how to do this math, but it certainly helps. Alright, so I think that covers everything on this first page. So we're going to move to the second page. There's a distance formula in 3D that is analogous to the distance formula in 2D. Essentially, if I want the distance from this point, x, y, z, that's here, to the origin, that's here, then this distance is given by this formula. And notice it looks exactly like Pythagorean's formula for distance, right? The hypotenuse of a triangle, if you got rid of the z squared. Right? And deriving this is really quite simple. If you start off in just 2D, and I look at this distance r, well, if this is x, this is a right angle, and this distance is y, then r squared is just x squared plus y squared by Pythagoras. And then now I am going to look at r and z. Alright, that height is just the z value. And so what I then have is that d squared equals r squared plus z squared. But this is just r squared. So d squared equals x squared plus y squared plus z squared. Take the square root of both sides and you wind up with that formula. Extending this to the distance between 2 points, if I have x1, y1, z1, x2, y2, z2, and what I mean by that is that one doesn't have to be the origin. If I want that distance right there, d, it's just the difference in the x values squared, difference in the y values squared, difference in the z values squared. Add them all up and take the square root, and you have the distance between 2 points. The midpoint, it's sort of a strange formula, but it's very, very nice in the sense that you're just averaging 2 points. So if you have these 2 points, we'll call this one point 1, which is x1, y1, z1, and this point x2, y2, z2. Alright, then the x-coordinate, and when I say the midpoint, I mean halfway from one to the other, that's the midpoint. And the x value for that midpoint is just the average of these x values. The y value is the average of these y values, and the z value is the average of these z values. So that's all you have here. That's averaging the x values, averaging the y values, averaging the z values, gives you the midpoint. Right? Alright, and so now that we have the formula for the distance between 2 points, I define a sphere. It's pretty easy. If you remember the sphere from, or a circle from 2D geometry, it just looked like this, right? And so in 3D, we're dealing with 3 variables, x, y, and z, so we get a formula that has a z term. And basically what that means is that if I have a sphere, it is really just the collection of all points that are equidistant to that center. Meaning if I have a point on here, x, y, and z, and the radius is r, then the distance from this point to the center, which is x0, y0, has to equal r. The distance has to equal r, or in other words, d squared equals r squared, and that's what this is. This is the distance from that any point on the surface of my sphere to the center of the sphere squared, and that's got to equal the radius squared. So that's my equation for a sphere. A little example, suppose I have a sphere, but I only have these 2 points that are endpoints of a diameter. In other words, I have 2 points like this, right? And they do pass through, when you connect them, it passes through the center. So I have my 2 points, P1 and P2 of a diameter. But getting the equation for this sphere is pretty simple, because if I just take the midpoint of P1 and point P2, that'll give me the center. And if I take that distance and cut it in half, that'll give me the radius. So let's worry about the radius first. The diameter is going to be the distance between those two, and then whenever I cut it in half, I'll have the radius. So when I take the distance between these 2 points, this point and this point, the difference in x squared, difference in y squared, difference in z squared, add them all up, take the square root. The distance of that diameter is 9, so the radius is half that, 4.5. And then the center is just the average of these 2 points. All right, so I take 4 and 0, average that, -2 and 5, average them, 2 and -2, average them, and I get a center of 2, 3/2, and 0. So my equation for the sphere is x minus 2 squared plus y minus 3/2 squared plus z minus 0, but z minus 0 is just z squared, equals r squared. All right. Equation for a sphere. Simple stuff. A few more examples in the exercises. So now whenever I talk about vectors in 3 space, they look very much like vectors in 2 space. In vectors in 2 space, I'd say something like u equals x1, x2, or x and y. Oh no, I know what I didn't use x's. If I have the vector as u, then I would just call this u1, u2. Right. But the key thing is there were only 2 terms because I was in 2D. For vectors in 3 space, I'm going to have 3 components for each vector. All right, an x component, a y component, and a z component. And specifically, a vector in space is defined identically as a vector in 2D. It's a standardized representation of all equivalent directed line segments in space. All right, in other words, if this is my space, then this vector is the same as that vector, 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 provided I was better at drawing vectors that look the same. All right, in the component form, suppose I have a vector that starts at this point and terminates at this point. Then the component form of v, that vector, is just q1 minus p1, q2 minus p2, q3 minus p3. Put the sort of triangular brackets in there, and you have the vector in component form. The properties are essentially the same. 2 vectors are equal if and only if all of their terms are identical. 2 vectors are parallel if one is a multiple of the other, a scalar multiple. The length, norm, or magnitude, and these all mean the same thing. The length of a vector is also called the norm of the vector, is also called the magnitude of the vector. Think of it however you want. You probably want to think of it in terms of the length of a vector, but I will often say norm or magnitude because I'm used to that. And it's used, again, just as in vectors in 2D. It's the double absolute value sign, and it's just the sum of the squares of the terms. And then you take the square root, and again, this goes right back to the distance formula we just saw in 3D, right? So if I have this vector here, all I'm calculating, if I want the magnitude, if this vector is v1, v2, v3, Then I'm just getting this distance from the end of this vector to the origin. So that's all that is. That's just the distance formula. When you add two vectors, you add them term by term. Scalar multiple, if you take a scalar or a number and multiply it by a vector, you multiply each term in that vector by the scalar. The magnitude of a scalar times a vector is just the absolute value of that scalar times the magnitude of the original vector. In other words, if k is less than 1, then ku will be shorter than u. If k is bigger than 1, then ku will be bigger than the original u. If I want the unit vector in a specific direction, I take my direction vector, v, divide it by its length, and this thing here is called a unit vector because it has length 1. Right? Length equals 1. Example in collinear points. This proceeds exactly as it did in the last chapter for 2D. If I have 3 points and I want to determine whether or not they are collinear, suppose I have P, Q, and R, the trick is to take PQ and then take PR and see if one is a scalar multiple of the other. If they are scalar multiples, they are parallel, and Q actually resides in there, or they all fall on the same line. Right? So the first thing I do is determine PQ just by taking 2 minus 1, 1 minus negative 2, and 0 minus 3. And then if I want PR, I just take 4 minus 1, 7 minus negative 2, and negative 4 minus 3 to give me PR. And if you look at that, it looks like I take 1, multiply it by 3 to get 3. I take 3, I multiply it by 3 to get 9. Things are looking good. It looks like PR might be 3 times PQ. But if I take negative 3 and multiply it by 3, I do not get negative 7. So they are not parallel, right? So the points are not collinear. How an example of a unit vector. Suppose I have this unit vector, negative 1, 2, 3. Looks sort of like this. I would go negative 1, and then 1, 2, and then 1, 2, 3. So it sort of looks like this vector here. If I want the unit vector in the direction of v, then I just take v and divide it by its length. But there's further request here. I want it in the opposite direction. So if I take v, divide it by its length, that gives me my unit vector. So it's this vector here. It has length 1. Then when I multiply it by negative 1, it goes in the opposite direction. So I have to find the length, but the length or the norm or the magnitude of v is just the square root of negative 1 squared plus 2 squared plus 3 squared. So that's the square root of 1 plus 4 plus 9, square root of 14. So that's the size. That's why I'm dividing by the square root of 14. So this part gives me the direction or the unit vector in the same direction as v. I hit it with the negative 1 and it sends it in the opposite direction. So that's what that vector looks like. This one down here. Alright. Do I have any more examples? Point the arrow. Yes. Okay, so here's the game. We did this game in 2D. We'll do it again in 3D. It follows the exact same process. So here's the demonstrative problem, right? Suppose I'm at this point P and I'm aiming in the direction of Q. I want to know what is the point 4 units from P in the direction of Q. So I'm starting at P, heading towards Q, and going 4 units. What is S? That's the question here. What is S? Okay, and so here's the standard process for this type of game. And this would be difficult if we were doing this in standard algebra with lines and things. It's easy with vector math. I'm going to take PQ, figure out what that vector is, right? I'm going to so that's this whole thing here. And then I'm going to divide by its length, which will give me the unit vector in the direction of PQ. And then I multiply that by 4, and that's going to be this vector PS, right? And then I'm just going to take P plus PS, so that's the point P plus the vector PS, and that will terminate at the point S. And there's a little abusive notation in that, officially speaking, P is a point, PS is a vector. I shouldn't be allowed to add them, but if you just add them term by term, you'll end up with a point, and that will be where PS terminates. Alright, so we're going to follow that procedure. It's really quite simple. We take PQ, that's just from subtracting, 7 minus 2, 12 minus 3, negative 2 minus 3, so there's my PQ. Its length is the square root of 131, that's just 25 plus 81 plus 25, square root. So I divide by its magnitude, then multiply that by 4. So this is that vector PS. Alright, now I just take P plus PS, and I get that point. So there's S. This is the point S. Easy stuff when doing vector math. Much harder if you're trying to define this with lines. And, like things like triangle, trig, and stuff like that. Easy to do with vectors. We're going to do a little bit. Oh, I forgot about this. Standard unit basis vectors. When we were in 2D, we had I and J. This was I, this was J. And they were the standard unit basis vectors. When we're in 3D, we now have an I, J, and a K, and they each have 3 dimensions, right? So that's I, J, and K. If you recall from Chapter 1, when we were in R3, we had E1, which is 1, 0, 0. E2 was 0, 1, 0. And then E3 was 0, 0, 1. It's the same standard unit basis vectors, only we now call them I, J, and K. Right? And with respect to what they look like, if this is my coordinate system here, my right-handed system, X, Y, and Z, then this right here, the unit vector in the X direction is I, unit vector in the Y direction is J, and then the unit vector in the Z direction is K. Alright? And if I want to express any vector in component form in terms of I, J, and K, it's just the first component times I plus the second component times J plus the third component times K. It is that easy. And going back requires the exact same process. For example, if I want to express this vector in component form, well, there's the 3 is the coefficient of I. There is no J, so that means there's a 0 in front of my J and negative 2 in front of the K. If I want to express this vector as a linear combination of I, J, and K, it's just 1I plus 2J minus 3K. It is that simple. All right. Okay, I want to go over a couple of functions in MATLAB. One I wrote and one that MATLAB is built into MATLAB. And so MATLAB's really good at a lot of different plotting and graphics. It's for some reason it's just not that good with vectors or directed line segments. It has trouble with a line with an arrow at the end of it. All right. So in the Chapter 2 program repository is this function called vectaro. And the usage looks like this. You put in the initial point, the terminal point, and the color, and it will go through the commands required to create a line and put an arrow at the end of it. And it starts at P1 and it ends at P2, and it'll make it whatever color you specify. Red, green, blue, black, things like that. And then if you just want to plot a point or a collection of points in 3D, you can use this command called plot3. That's built in. The trick is you have to remember to you have to insert your arguments, all of the x values, y values, and z values. All right. the other way you could do this, you would think you could do the x1, y1, z1, x2, y2, z2. It doesn't work that way. You have to do all your x's, then all your y's, and all your z's, and there are reasons for that. It's actually a lot easier, but there's a temptation to do it the other way. So just remember, you have to put your x values in, comma, y values, z values, and these are actually vectors in a MATLAB sense. They have square brackets. All right, it's a matrix, really. It's a one-dimensional matrix. Okay, and so we will create, and by the way, there's this function file is in the program repository. It's called plotting vectors. You should probably open it and run it and play around with it. But what it does is, the first thing it does, it plots an arrow from this point to this point, right? And then it plots a vector that represents that directed line segment, and then it plots the point where that vector terminates. Right? And so the commands used specifically, I have up here, and I want to use it because here's the graph. So this first one, it is a directed line segment from P1 to P2. And the way you do that in MATLAB is you use that vectaro command. Make sure that function file is residing in the same folder you're currently working. There's P1, there's P2, there's my color. It creates a vector that starts at P1 and terminates at P2. Once you convert this to a vector in standard component form, you're subtracting P1 from P2, so that's 0 minus negative 2, 1 minus negative 1, 4 minus 2. That's the vector u. And then to plot that vector, again, I like it to have an arrow, so I'm going to use vectaro. Starts at 0, 0, ends at 2, 2. So this u vector is also representative of that same directed line segment up there. But now suppose I didn't want an arrow or a directed line segment. Suppose I wanted a point. I just want to plot the point 2, 2, 2. I use this command plot 3. There's my x values. It's only 1. Y values, z values. This makes a red circle. This increases the marker size. This makes the marker face color blue. That's this blue right there. So what you have is a red circle with a blue interior. So there you go, directed line segments, vectors that start at the origin, and a point. They're basically created the same way within MATLAB, only to get the directed line segments and the vectors, I want to use this vectaro command purely because I want to get that arrow at the end of the line. Alright, so that wraps up Chapter 2.2. Again, don't be afraid to go to the Chapter 2 repository, grab this file, and play around with it. Change these values, see what they look like. You can rotate the 3D graph to see how it looks as you move it around. But that's all. I will see you in Chapter 3.3 if you are so inclined to join me. Bye now.